Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on overview of experimental stress analysis. In the last class, we had quickly reviewed what is Moire, then we moved on to the technique of brittle coatings. And in brittle coatings, I emphasized you load the model incrementally, and at every stage of load you go and record the crack pattern and also mark the ends of the crack pattern. Both give certain kind of information for you to post process the data. And I also mentioned when you have a very large structure, brittle coating is an ideal approach to identify zones where you have to concentrate for further investigation. And if you look at combination of brittle coating and strain gauges makes the stress analysis lot more accurate and fast, because in a large structure you do not know a priori which are the zones that needs further attention, which could be identified by brittle coating, followed by a strain gauge technique can give you accurate numbers in zones of importance. Then we moved on to holography, and I explained what is the fundamental difference between normal photography and holography. In normal photography, you record only intensity information. In holography, you record intensity as well as the phase information, and the phase information is recorded in the form of interference fringes. And we also saw the difference what a normal negative looks like and how does a hologram looks like. A normal negative you can make out what is recorded with visual inspection. On the other hand, when you go to a hologram, you see interference pattern, you do not see anything beyond that, and you need to have a separate optical arrangement to reconstruct, only then you can see the hologram. And one of the very common application of hologram is on hologram stickers. You all are familiar, where what you find is, if to testify the genuineness of the product, almost every product you name it, they have a hologram sticker. The reason is holograms are difficult to record, but easy to reproduce, and this helps you to make it as a sticker, and only the manufacturer, genuine manufacturer, will have the original for him to use it as a sticker. So, it acts like a security device. But what we find is, from a stress analysis point of view, we are not interested in only the use of hologram stickers, we want to get quantitative information. So, for quantitative information, what you have to do? You have to go in for hologram interferometry, and let us look at what is hologram interferometry. So, what you find here is, you will have to look at that what is the difference between classical interferometry and hologram interferometry. In your schools, I am sure you must have done the exercise on Newton rings, where you essentially use optically polished surfaces and find out unevenness by a interferometry technique. So, classical interferometry was limited to measurements of small path length differences of optically polished and specularly reflecting flat surfaces. So, the key point here is you are looking at flat surfaces, they were polished, and you are also confining your attention to small path difference. So, even a mercury arc lamp is sufficient to reveal that kind of information. And in fact, when holography was developed in 1948, Gaber had only mercury arc lamp. So, the technology was not sufficient to exploit the full potential of holography at that time. It is only after lasers were invented and were available for common use, the interferometric techniques had a boost. And what we look at as hologram interferometry, what you find here is, what we find here is the earlier mercury arc lamp had monochromaticity is not to the extent like what you have in laser, and coherence was also limited. So, we were confining only to small path difference. And what happened in hologram interferometry was extension of classical interferometry to 3-dimensional diffusely reflecting objects with non-planar surfaces became possible. So, we have had a quantum jump, we had a flat surfaces, from flat surfaces we could go to a 3-dimensional objects, and once you come to 3-dimensional object, the path length is not small, path length is much larger, and we are also looking at non-planar surfaces. So, you graduate from simple experiments on interferometry and to go and find out what happens on a 3-dimensional object. And in hologram interferometry, you collect so much information, the processing becomes difficult. It is not that the technique is bad, the technique collects so much information, because you are looking at 3-dimensionality in all its totality. Okay. So, this was possible mainly because of lasers. Lasers have helped this possibility. And what you have is, you can classify hologram interferometry into various methods. One of the earliest one was double exposure hologram interferometry. The name itself suggests that you are going to have 2 exposures. When you are going to have 2 exposures, you will not be able to see the fringes in real time, because you have to post process these exposures, only then you will be able to see the fringes in real time. And what we saw in photoelasticity, we could see the fringes as the model was loaded. The similar thing was also there in Moire. When I move the fringe gratings relative to each other, I started seeing fringes. I did not have to have 2 exposures for me to see the fringes. So, what you find here is, in double exposure hologram interferometry, it is simple, but one can see fringes only after recording. But what you will have to understand is, in holography we talk in terms of wavelengths. So, I can measure very small displacements. So, it is a very fine technique, and later on we will also see there is also stringent vibration isolation requirement for many of these techniques. Why that is so, that also we will have a look at it. So, the other category, see, once you find a restriction, researchers do not keep quiet. Researchers find out ways by which they will circumvent this limitation. So, what you have is, you graduate from double exposure hologram interferometry to real time hologram interferometry. The name itself suggests you observe fringes while the model is loaded. So, it is lot more convenient. Real time holography is lot more convenient than double exposure hologram interferometry. But if you look at the technology, you will have to be very careful in handling it, because you measure in terms of wavelengths, even small misalignments between exposures can spoil your quality of output. So, this is very important. So, whenever you find a restriction, researchers and scientists work and circumvent this. So, if you have a problem, do not get worried, you have a scope for research. That is how research problems are coined. Okay. And what is another form of holography is time averaged hologram interferometry, and this was useful for recording mode shapes in vibration measurement. Time average itself says you are having a vibration event, and then when the model is vibrating, you have to have some kind of a time post processing, so that you get the information without a sense of blur. Okay. And here you get Bessel fringes and so on and so forth. So, what we find here is hologram interferometry can be broadly classified into 3 categories: double exposure hologram interferometry, real time hologram interferometry, and time averaged hologram interferometry. When you look at the development, what you find here is hologram interferometry's first application was on finding out the mode shapes of a vibrating object. So, if you look at one of the motivation for hologram interferometry to see as a stress analysis or displacement measurement tool, it was initially used for capturing the mode shapes of turbine blades, and Carl Stetson and others have contributed significantly in this area. And we have already seen, when you say holography, I look at the depth information, and in the case of vibrating blade, you essentially find out out of plane displacement. So, the natural extension of technique for measuring depth information is used for finding out of plane displacement, and that is a natural extension of holography. But interpretation is quite complicated. Why it is complicated? Quantitative analysis of fringes is quite complicated because we record lot of information than what we can handle, because you are looking at from planar surfaces to arbitrary curved geometry, and then you want to find out. So, you will essentially find out the displacement vector. It will have a component of u, v and w displacement. It is not that there is deficiency in the technique, it is mainly because the information that is recorded is much more than for you to process, and this we will see again and again. Quantitative analysis of fringe is quite complicated. We will keep looking at it as long as we look at hologram interferometry as well as speckle interferometry. But what is the way that we can circumvent this? If I choose appropriate optical arrangements, holography can be used to find the complete displacement vector or specific components or displacements of the deformed object. So, this is what I said. First, identify what is the problem. Once you identify this is the problem, then address it and find out what all you can modify, and then how you can use the technique. So, what you find here is I can get the complete displacement vector, more than complete displacement vector, specific components or displacements of the deformed object would be very interesting when we want to even understand analytical solution. Suppose I want to know what are the displacements in the case of a cantilever. I would like to see only u displacement and v displacement. So, I will have one optical arrangement to get u displacement, another optical arrangement to get v displacement. Then I can compare it with my analytical solution and see that these two match. Whereas, in Moire you had a very simple process wherein the grating direction dictated your data interpretation. Here you have to provide some constraint on the way you do the optics and some constraint on the specimen deformation, because we are not bringing in a 3-dimensional object and then extracting UVW, extracting only u displacement. In a 3-dimensional object, when it is deformed, you will get UVW in general. Here you take a 2-dimensional problem and then deform it and extract only u displacement or v displacement as the case may be. So, you have to know while doing this experiment what are all the restrictions in the way you have to do the experiment. And what we have been looking at is, we have also looked at how some of these techniques can be combined. We have looked at brittle coating can be combined with strain gauges, so that I get information on the entire surface and also detailed precise information in regions of interest. On similar lines, I can use a variation of holography. I choose an appropriate optical arrangement to get only the lateral displacement, and you all know the lateral displacement, what you have as lateral displacement if I have this as a specimen and because of Poisson effect the specimen has lateral displacement in this direction, if I look at this, that could be related to in a planar problem to sigma 1 plus sigma 2, that is how the whole thing comes. Holography essentially gives you the depth information. Suppose I have this as a specimen, when I deform it, when I pull it and deform it, you will have thickness variation. Thickness variation could be related to sigma 1 plus sigma 2. So, when I record that as a whole field information, I call those contours as isopatchics. So, this is where holography comes. Holography essentially measures the thickness information, depth information can find out. Here I find out the change in the depth because of in plane stress. I call those whole field contours as isopatchics, they are nothing but sigma 1 plus sigma 2 contours. And what photoelasticity gives? Photoelasticity gives you sigma 1 minus sigma 2. So, now I have said individually it will give only a particular contour or a contour which has combination of stress components, but if you want to post process I can extract them individually also. So, that is what is summarized here. Isopatchics, contours of sum of principal stresses can be recorded by holography, and in conjunction with photoelasticity one can find individual stress components.
Actually, in holography you told about the isopatchics, that is sigma 1 plus sigma 2. I did not understand the concept between how sigma 1 plus sigma 2 is a measure of the thickness.
See, in the case of photoelasticity essentially we deal with planar models and subjected to in plane loads. So, when you have that kind of situation, when I have a planar model, suppose consider that my hand is the model, then I pull it, what happens is because of Poisson ratio effect the thickness changes, and if you look at the thickness change, it is proportional to minus nu times sigma x plus sigma y divided by E, and sigma x plus sigma y is the first invariant and sigma 1 plus sigma 2 is also first invariant. So, from there you get sigma 1 plus sigma 2, it is simple, it is straightforward. I get sigma 1 minus sigma 2 from photoelasticity, I combine these two and get sigma 1 and sigma 2 separately. But the basic question here is, do you require individual stress components for the problem on hand? If you require it, then go to the circus, because holography is not a simple exercise. Any interferometric technique is not a simple exercise. So, this is where I said, I also showed you the picture of Athena, goddess of wisdom. So, you should be wise enough to tackle your problem, not blindly use one technique, another technique, collect volume of information and do not know what to do with it. Okay. So, this is where wisdom is required. And what is the restriction in holography? Holography demands vibration isolation. So, we will have to have a look at what is the optics that I use and why it dictates vibration isolation. If you just look at how a double exposure hologram is made, you will be able to appreciate why in holography we talk of vibration isolation. We have never spoken about vibration isolation in photoelasticity. On the other hand, I caution in Moire you will have to worry about rigid body, displacement and rotation. Translation and rotation you have to worry about, because that can give you spurious fringes. So, there also the alignment becomes important. When once you come to holography, you find vibration isolation is a very important requirement. And even this, with advancements, people are coming out and making techniques which are reasonably robust. That is also research is going on. And what you find is, because you talk in terms of wavelengths, you can record minute displacements and such tiny components as MEMS. They are nothing but micro electromechanical systems. So, you have even the actual component is very small in size, and if you want to find out the displacement on that, they will be much smaller than this. And because hologram or holography helps you to measure displacements of the order of wavelengths, you can measure those small quantities comfortably. If I have a very small component, I can't go and paste a strain gauge. Though strain gauge gives me 1 micro strain, the strain gauge will go and reinforce the small component. So, I should go for a non-contact measurement. So, when I have to go for a non-contact measurement, holography is good. So, what you find is its ability to measure even minute displacements of the object is its strong point. An interesting use of holography on measurements of MEMS is being reported now. We will also see one example in the course of the lecture. And what we have now is, we will go and look at what are the steps in a double exposure hologram interferometry. Because I said vibration isolation is very important, and when you say vibration isolation is very important, you will have to know what are all the components in a general holographic recording, and we will have a look at it. We will also have a enlarged portion of it. Okay. So, what I have here is, I have a light source, I have a next component as spatial filter. This spatial filter has a pinhole and also a lens. Then I have a beam splitter, then I have another lens, I have 2 mirrors, and I have a object to be recorded for the hologram, and I have a holographic plate. You need to sketch this, and we will see the optical diagram. What we will do is, I will have to do 2 exposures. I will make exposure 1, I will also show exposure 2. So, you need to have a decent sketch of it. It will take you few minutes for it to do it. Take your time, because this is important, and I am going to show this in a slow motion, in the sense, light travels at a very high speed. So, I am going to draw the diagram, and then I am going to show as if light moves, but it is at a very slow movement. And what I will do is, I will make an exposure 1. Just look at what happens. Light comes, hits the beam splitter, and goes to the mirror arrangement and comes to the hologram, and this is a reference beam, and from the beam splitter another set of rays go and illuminate the body, and this also comes to the hologram, and both happen simultaneously. For the purpose of understanding, I have shown how the reference beam falls on the hologram and how the light reflected from the object falls on the holographic plate. After you develop the holographic plate, it becomes a hologram. You can see the hologram. So, what you have here is, you have the laser light source, you have a spatial filter, you have a beam splitter. So, beam splitter sends one set of beam to the hologram directly, holographic plate directly, you call that as a reference beam, and the necessity of a reference beam brings in the restriction of vibration isolation. If I do not require a reference beam, then I do not have to worry about vibration isolation. Because of the reference beam, I need to conduct experiment as carefully as possible. See, one of the requirement is, even a normal running AC can alter the vibration characteristics. So, people keep the also AC away from the holographic table, they do not keep it near it. So, you have to take care of that, and I will repeat the exposure 1. You can just have a look at it, how the whole exposure takes place. So, you have a reference beam, and you also have a beam reflected from the undeformed body. So, these 2 waves interfere, and then I get this pattern. So, if I see this pattern, what I will see? I will see this 3-dimensional object. If I record this as a hologram, develop it and then reconstruct it, I will see the 3-dimensional object, and here I am not interested in knowing the metrology of the 3 dimensional object, I am not interested in the depth measurement or shape measurement of that object. I am interested because of loads applied, what is the deformation introduced in the model, that is what my interest. So, that is why you need a double exposure. So, what you do is in the first exposure you capture this. Now, what I do is, let me see whether I can do the second exposure. I have a button below, I will carefully press it. So, when I do the second exposure, you would have noticed I have not changed the reference beam, the body is deformed, and the deformation how I obtained I have not shown it in the figure. I have only shown that this is a deformed body. So, you have the light reflected from the deformed body is also recorded in the same hologram, same holographic plate. Now, when I develop this plate, I will be able to get the fringes which is representative of complete deformation of the 3 dimensional object. That is the advantage of holography, because you record so much information, interpretation becomes involved. Once you find it is involved, there are enough number of research students and research scientists across the world who try to crack this problem. So, that work is going on. To a large extent we have achieved. In certain issues you have to have certain complicated calculation, that is fine. And let us now repeat the exposure 2, then we will see the entire animation again. So, in the exposure 2 I have a reference beam that is not altered, I deform the body and I record another set of light rays on the holographic plate. And if we go in the sequence, we will see the exposure 1. So, only during exposure I have a reference beam which falls on the holographic plate, that is not disturbed when I go for the exposure 2. So, in between the exposure I have to deform the body. There are certain aspects that you will have to note down, how do you deform and what is it that you need to practice, all that we will see. Right now you look at the optical diagram and find out how the whole aspect is done. So, this illustrates that you have a reference beam and you have undeformed body, and then you have this second exposure. Second exposure is done where I have this light rays come from the deformed body. Now, we will look at what are all the restrictions that you will have to look at when you are loading the model. See, the specimen is loaded and the second exposure is made, that you have well understood, and this is to be done what? This is to be done in darkness, total darkness, okay. And you have to ensure nothing of the optical arrangement can be disturbed between the exposures. So, it is not that you simply move your hand and then I mean disturb the alignment of any of the optical elements. This has to be done very carefully. So, that is what I have always been saying, experiments are planned and executed. It is not that you go quickly make some measurement and come and interpret the way you do it. Experiments have to be carefully planned. Also, you anticipate what is the type of result approximately. There may be error in judgment, but still you want to know the range, that is how you want to do the experiment. So, you can't disturb optical arrangement. And what are the other finer points? The object has to be mounted suitably so that it can be loaded without disturbing the optical setup, and loading has to be done in dark. Even this you can practice. The other difficult point here is since you do not know a priori how the fringes are formed, you will have to have appropriate calculation to find out what is the extent of load that you should apply. And what is advised is you have to do rehearsal of the steps in applying the loads first in the light and then in darkness is desirable. So, you have to do some practice. So, when you want to record a hologram, you have to do this practice, and from loading point of view, since fringes won't be visible while applying the load, choice of suitable loads to generate sufficient fringes has to be calculated a priori or repeat the experiment until satisfactory results are obtained. So, you understand experiments are not that easy, it is back breaking, that is why people want to minimize the number of experiments that they want to do. The numerical simulation have to be looked at more in the light of reducing the number of experiments, because experiment is truth. Ultimately, any design that you want to release for the public, where any design deficiency can have serious consequences, you have to testify the results verified by experimental measurement. But experiments have to be done systematically, it takes time, until you get satisfactory results you may have to get it. This is where people found that why do you have to go and do this kind of double exposure. With advancements in computer technology, people are able to solve and address these issues reasonably well, and even now though there are restrictions, digital holography is also catching up. And what are the other things that you will have to look at? Because I said you are recording more information, reliable quantitative interpretation of holographic fringes is still difficult. There is no general method, but for specific applications interpretation is possible. See, one of the emphasis on many of these optical methods is people would like to minimize human intervention. What they want is they want to press the button and then finally say that this is the displacement, deformation, so on and so forth. In fact, I do not subscribe to that kind of a view. You need to use computers more for doing the routine job, but intelligence, human intelligence has to be used. Replacing human intelligence totally by any of the automated methods can result in absurd answers many times, and also the effort involved is quite high. Okay. So, what we find here is data interpretation is an issue, and what we will have to do is, when I want to do for specific applications, I said already the specific application is determining isopatchics. The optical setup should be adapted to the problem to simplify data interpretation. So, finally, what do you come down to? Planar surfaces are easier to handle. So, though you start with 3-dimensional surfaces, 3-dimensional displacement, I can record the information, but interpretation becomes difficult. But I will also say, when I have 3-dimensional information, it is very rich, and we will also see a separate lecture on how to extract as much information as possible by looking at fringe patterns alone. We will have a lecture on that. But once you come to any one of these experimental methods, the optical setup should be adapted to the problem to simplify data interpretation. A generic approach is still elusive and difficult, specific applications are possible, and you adapt the optical arrangement to simplify data interpretation. Now, what we do is we move on to another technique, that is Speckle methods. And this is where it is, you have a very nice illustration of the method. You just see the speckles first, and these are all the laser speckles, and this is just to give you a feel of what the speckles are. I have shown this animation. And obviously, this is an offshoot of hologram interferometry, and we have already seen whenever you have a coherent illumination, you have formation of speckles. We have seen, if I use it with white light, Athena goddess was looking nice. The moment I illuminate it with laser, you saw speckles on the face on the entire picture, and this is used as a technique to reveal displacement information. And what you find here is the speckle distribution is random, but the advantage here is they are temporally constant and are spatially determined. This we will see again and again. We will emphasize these two aspects, that is, this is why we are able to use it as a technique. If they are totally random and changes as a function of time and space, we will not have speckle interferometry. What we find here is you have randomly distributed speckles in space, they are irregularly shaped, however, they are temporally constant and spatially determined. And why is speckle interferometry is advantageous? The main advantage of the speckle interferometry is its adaptability to digital data acquisition by modern CCD cameras. So, speckle methods is an offshoot of hologram interferometry, and speckles are random, irregularly shaped, but they are temporally constant and spatially determined. This is a very important characteristic which we use it to our advantage. And also you will have a lot of debate in literature between the methods will look very similar. There is a still debate whether to call it as speckle interferometry or TV holography. This kind of discussions are going on among academic circles, and then this such discussions will continue to exist. So, we will see certain category as holography in our own judgment, certain category as speckle methods. And what we need to look at is, we need to look at what these speckles are. So, what I am going to do is, I am going to look at how speckles are formed. And one of the important aspect in all this category is, you have formation of objective speckle. And what I want to show here is, surface is rough at the scale of wavelength of light exaggerated. So, make a sketch of the surface. The surface for all practical purposes will be very smooth and straight, but if you look at the wavelength of light, surface is rough at the scale of wavelength of light. So, it is a highly exaggerated picture. It is a very highly exaggerated picture of the surface to illustrate how speckles are formed, and it is very interesting. This will open up deeper understanding on how you have these methods. So, and what I have is, I have a source of light, and then it is going to impinge on this, and you can observe it very carefully. That is what I said, all these animations are very slow, it is not at the speed of light. So, okay, this is just to understand the sequence of steps in the formation, and let us see that. So, what I see here is, as the light hits, you have light scattered at each of these points. So, what I have is, we can also see this little enlarged. Instant light scatters over the specimen surface. So, when it hits the specimen, the light gets scattered in all direction, and this you will see again. Okay, we will see the animation, the light will hit other places on the object. What you need to notice is, the light ray comes and immediately you have scattered ray, and scattered light do not stay here, they travel to the screen. I have not shown that portion, I am showing the sequence of happening in stages for you to understand. And what I have here, the light ray comes here, then you have immediately scattering of light, immediately here you have scattering of light, and this is what happens. Now, what I am going to do is I am going to put a screen, and this screen is sensitive to whatever the light that falls on it, or I should have a CCD camera with its lens removed. I do not have a lens in this process, I do not keep a lens here. And what will happen is, and this is what you will have to look at, see, this is again a very important point, any point in the screen receives light from several sources of light scatter. This I want you to observe. I am looking at objective speckle, and one of the key point here is any point in the screen, receives light from several sources of light scatter, and that you see the animation. Okay. And I am looking at a point like this here. So, I have a light coming from this scatter, another ray coming from this scatter, another ray coming from this scatter, another ray coming from this scatter. And it so happen I have selected a point, so happen that these rays do a constructive interference, and I see this as a bright spot. And I take another illustrative point, where again I will have light rays from all the scattered points. This is the key point, any point in the screen receives light from several sources of light scatter is an important characteristic of objective speckle. So, what I do is I see the second set of rays meeting at a point, and I have selected this point in such a manner for illustration that these rays interfere and gives you dark fringe, dark point. So, I have a bright point and I have a dark point. Have you been able to make a reasonable sketch of the final ray diagram of the whole thing? Because you need to have this. We have seen how this formation of lines actually happen. The light rays go and hit the model, on the surface of the model it gets scattered, and from the scattered all the any point on the screen receives light from several points of scatter, and that is how you have to read the picture. You may finally have a picture like this, but how this picture came into existence, these are the sequence of operations. And if you want, I can repeat the animation once for clarity. You just see only animation now. I have a light source, light comes and hits it, you have scattered from each of these points where it meets the model. Then I put a screen, and each point on the screen receives light from several sources of scatter, 1, 2, 3, 4, for all this you get a ray, and this is a characteristic of objective speckle. I will also go and see another formation of speckle, I call that as subjective speckle, it is known as subjective speckle, there the story is different. And what is the advantage of this? Provides the basis for understanding the formation of speckles, and it is difficult to observe. Why it is difficult to observe? All of us have an eye which has a lens. The moment I have a lens, I always observe only subjective speckle, we will see that also, because I have a lens, my eyes have lens. So, the moment I put a lens, though I record something, whatever the specular reflecting object, if I look at directly, I would be recording only subjective speckle, but only on a photographic plate, or you have to take special effort to record objective speckle. So, it is difficult to observe, and this is what the methodology is given, what way I can do expose a photographic film or a CCD array without a lens. The recorded pattern will be affected by the film characteristics or the pixel size and its spacing, has little practical applications, but the importance here is it provides a basis for understanding the formation of speckles. But it is difficult to observe. So, you need to have a photographic film exposed, okay, and that is how you have to do it, and this shows how the whole speckle gets formed, and this shows the animation again. Because if you understand this, then your appreciation of speckle methods become lot more clear. So, I have a dark fringe formed, I have a bright fringe formed, and I get light from all points of scatter, and the points are summarized one after another. You understand that it helps you to understand formation of speckles, difficult to observe, and we finally say that it has little practical applications. Now, we will see what is subjective speckle, and what we are going to look at is we will just make one small modification in this, rest of it is same. The first procedure is same. In fact, you can even have another sketch here wherein you modify it, you do not have to repeat the full sketch. The moment I go to subjective speckle, the difference is in between the screen I put a lens. Lens is the key aspect. What happens on the surface, it is same like what was seen in objective speckle, but what is recorded, there is a subtle but important difference, and subjective speckles are very useful. We want subjective speckle, Speckle interferometry uses only subjective speckles, and we have an advantage. And let us see how the formation of speckles here. Because of the lens, what happens? Because of the lens, what is the key point here is, suppose I have a point on the object, it is mapped onto another point on the screen. That is what the lens does. In the case of objective speckle, this point will receive light from all points of scatter. Because I put a lens, this will receive light from a corresponding point on the object, and in this case I have taken that these two rays interfere in a manner that you have a dark fringe, dark point. I would not call it as a fringe, I would call it as a dark point. Similarly, for this another point, if I take it, what I am going to have is, I am going to have, I will choose the point in a manner that there is constructive interference and I have a bright point. So, this is the fundamental difference, and what is important here is waves scattered from any single point of the object or focused to a corresponding point of the image. That is a fundamental difference between objective and subjective speckle. So, when I come to subjective speckle, use of lens is the key aspect, use of lens is the key aspect. And let us see, now what I will say is, I said that objective speckle was difficult to observe and subjective speckle is nice to see, and if I have a film, what I will have is, I will have this formed here, I have the speckle beautifully formed here. I have the speckle beautifully formed because I have a lens, and we have already seen that it is temporally constant, as a function of time it does not change and spatially determined. It is like a fingerprint, the same concept I will again reinforce, we will have a look at this in the next slide as well. So, the key point here is wave scattered from any single point of the object or focused to a corresponding point of the image. That is a key difference between objective and subjective speckle. So, I have beautifully formed subjective speckle pattern, and when I go and look at the finer aspects of it, it is like this. So, what we summarize here is all pictures taken with coherent illumination contain speckles. This is a fundamental point that we have been looking at. An observer who looks at the object surface perceives subjective speckle as a human eye as a lens. This is what I also mentioned it earlier, and you have this speckle, and what is put here is speckle brightness is random, and what you find is brightness at one point bears no relation to the brightness at any adjacent point. So, speckle brightness is random, these are all the characteristics of it, and what I find here is it is put in a slightly different words, set of words, this because this is very important characteristic. So, repetition is always advantageous for you to remember. Speckles are irregularly shaped and are distributed randomly in space, it is temporally constant and spatially determined, and also I find each surface structure generates its own speckle pattern. Suppose I have a, if I change the structure, the speckle patterns also will be different. Thus, the speckle pattern provides a fingerprint of the illuminated area. It is like a fingerprint. In the case of moire, we put a grid on it which is regular. In the case of speckle, you have these speckles formed that act like a fingerprint, and that is why we also said speckle provides you fringes which are not very smooth. We saw that when we looked at out of plane displacement of a plate clamped all around the boundary with a central load. When you have a plate all around the boundary and put a central load, when we looked at the out of plane displacement, the experimental fringe pattern which I showed was from speckle interferometry. It was not as smooth as what I saw in photoelasticity, it had only points. So, this is, they are called correlation fringes, different from interferometric fringes, and there is also a reason why we looked at moire first and then look at holography and speckle interferometry, because speckle interferometry has certain ideas shared with moire. You have a random pattern which is naturally produced because of specular reflection.
Can speckle methods be used for surface measurements?
Definitely. See, all these techniques, optical techniques like holography and speckle, they are all used for metrology applications. Metrology application is happening parallelly, and what we are interested in this course is to look at, under the given application of loads, what is the deformation introduced on the object. And in fact, if you look at the future, you are going to have 3D facts. The concept there is, you will have an object, you will have a facility like your microwave oven, you will have a facility, you keep the object will rotate, and you will have light rays scanning the object and pick out the coordinate information, and this will be available in a file that will be transferred over internet or any type of data transfer mechanism. At your end, you will have a rapid prototyping machine which will understand these signals, and you will have the object on hand. When you print it, you will have the object on hand, and this is what people say that is going to be the future of manufacturing, and it will also reduce your inventory, and developing nations, they would like to concentrate more on design and make the underdeveloped or developing nations to do the manufacturing. And in this lecture what we started was we looked at what is holography, and we focus more on holographic interferometry, because holographic interferometry is necessary for you to make the displacement measurement, and we graduate from planar surfaces to 3-dimensional objects. But when we graduate, there is also a difficulty comes across, because I record more information, data interpretation becomes more challenging, but for simple planar surfaces it is possible for you to do the data interpretation by appropriately constraining the model and also looking at the way the model is loaded. Then we moved on to speckle interferometry. In speckles we understood that you have, when you have coherent illumination, speckles are formed, and when I say speckles, there are two aspects people look at it, what are known as objective speckle and subjective speckle. We saw the difference between objective and subjective speckles, and now we have to go and see what do I get in speckle interferometry, and then what is the variation of speckle interferometry which is adapted to an industry which we call it as shearography, and why it is advantageous to an industrial environment. We have looked at in hologram interferometry, when you do the double exposure you have a reference beam. The necessity of a reference beam demands vibration isolation. When I come to speckle interferometry also we will see you need a reference beam, but on the other hand when I go for shearography I do not need a reference beam. So, it is robust from an industrial point of view, and NDT people have quickly taken this for inspecting honeycomb panels. So, what you will have to appreciate is when you develop any of these techniques, whatever that is convenient for industrial use automatically comes out. People identify that, and that becomes a very popular technique, and people are able to use it day in and day out, because the technique that you want to use should be robust. It should not be sensitive to the person who conducts the experiment, and vibration isolation is a very key aspect, and if you do not have vibration isolation you will not be able to record holograms. Thank you.